let's say the same wooden plank is now placed on top of two fluids so that it kind of looks like this. Let's say we have water, and for some reason, let's say there is some layer of fluid here. Let's say the density here is 1 gram per cubic centimeter. The density here is let's say I'm going to do it like this. I'm going to say, imagine there is something here with a density of 0.3 gram per cubic centimeter, some fluid that is very little, that has very little density, or I could have made this more and made the plank more. So now what's going to happen? The plank is going to sink Okay, so the plank is basically going to sink all the way through this fluid. For the sake of other than let's just call it oil, or whatever oil it is, it's very little density. Okay, so it's going to sink through the oil and then it's going to penetrate into the water. So remember the original height of the wood was 12 centimeters. Okay. So let's say this one is 8 centimeters. The oil's height is 8 centimeters. The wood is 12. So how far down is the wood gonna go? Is it gonna go all the way down, or is it gonna stay up? Because it's also gonna be supported by the water. Okay. So it could be that maybe the wooden plank goes all the way through and penetrates all the way through the oil, but maybe not, because the water is also pushing up on it. So we could still use Archimedes' principle here, but we have to now say the two buoyant forces are provided by the water and the oil. That's going to equal to its weight. So the weight of the F buoyant provided by water plus F buoyant provided by oil, for the lack of the better term, let's say that was the oil, and then that's going to equal the mg. So so then we're going to add the buoyant force of the water, which is the density of the water times the volume prime, plus the buoyant force of the object on the oil on the object. So that's going to be the density of the oil times, I'm going to call this volume double prime. So the volume of the object which is inside of the oil, and the density of the object times the volume of the object, and then both of these have g's, g, and the g cancels, and you basically get that. So the density of the water is 1. The volume of the portion of the object that is sunk in the water, well, if it is a cubical or rectangular object, we are assuming then that's just basically equal to the height of the portion of the object that is sunk underneath the water times the surface area A here, this surface area. So we really don't need it's basically a cross-sectional surface area. So we really don't need the A, because the A appears all the way through. This would be a harder problem if it was a spherical object or a different looking kind of object. So it'd be just H prime plus density of object, which would be, this is the density of the oil, which would be 0.3, and that would be 8 centimeters, and density of object, which would be 0.4, and the volume of the object, that would be equal to 12 centimeters. Okay? So the H prime over there is going to be 0.48 minus 0.24, and H prime is equal to 0.24 centimeters. So that's not a lot. It only penetrates 0.24 centimeters into the water. Okay? So basically it looks like just barely penetrates inside of the water, 0.24. And then of course all 8 centimeters of it is here. And then how much of it is there? Well, then you would just do 12 minus 8 minus 0.24, 3.76 centimeters. This would be, if we go look higher, it'll be 3.76 centimeters. So only 0.24 would be under in the water. How about if the wood was more dense? Let's say the wood was 0.6, 0.7, 0.8. Well, now it's going to start sinking more. What should its density be such that the top portion of the wood be flat with the oil, so that it will look like this? So you could kind of ask any kind of question with that. Okay, what would its density be? Well, then basically you would have density of the water would be 1. H prime, well, H prime would be what here? The portion of the wood that is sunk under. Well, if the whole thing is 12 and this thing is 8, then this thing would be 4 centimeters. So H prime would be 4 now. Density of the oil would be 0.3. This would be 8. Okay? And then here would be density of the object is still 0.4 times the height of the object is still 12. So sorry, I meant to say the density of the object, we should put here density of object, because this one is actually getting confused with the oil here. Right, so you have to always be careful for OO so you don't get confused. This is density of water, density of oil. Now this time we don't know the density of the object. Okay, so we're going to have density of object is an unknown, and the question was what should the density of the object be so that its top portion is flush with the oil. So now you're going to end up with 4 plus 2.4 divided by 12.53. Oh, that's not really that much. Density of object is going to be 0.53 with a bar over it, gram per cubic centimeter. So instead of 0.4, if it was 0.53, it would go like that. Now, if it goes more. Well, of course, if it's the same as the density of water, it'd be exactly flush with the water. So what if the problem said, what should the density be so that it's halfway? It goes halfway through the oil. And you can see it could be worded anyway. Halfway through the oil, well, this one would be 4. And then this one has to be what? Well, if this is 4 and the whole thing is 12, right? Then this would be 8. So this would be 8 right here, because 8 plus 4 has to be 12, right? So now what should the density be? So this time you will sink halfway into the oil. So you have 8 plus 0.3 times 4 is 1.2 divided by 12.77, or with a 0.76 with a bar over it. Okay? So you can see what's happening here. You go halfway into the oil, and then after that it starts sinking more. Okay, now let's do cases with sinking objects.